we have seen some examples of vector spaces, and I would still like to see more examples. So, this example. In this example, from a given family of vector spaces over the same field K, I will construct a new vector space which will be called as a direct product, and then we will construct another one which will be called a direct sum. So, the title of the example is direct product and direct sums. Of vector spaces. So, let K be a field and Vi, I in I, be a family of K vector spaces indexed by the set I. In this case, I could be finite or I could be infinite also. So, I is arbitrary. So, on each Vi, we have each Vi is an abelian group. Strictly speaking, for each I, this abelian group structure on Vi would be different. So, strictly speaking, I should write some suffix I. These are abelian groups, and each of them has a scalar multiplication. Each of them has a map from K cross Vi to Vi. These are called scalar multiplication. And let me remind you that we are denoting the same A comma Vi going to AVI. So, it is clear when we write a scalar multiplication which vector space we are doing the scalar multiplication. So, now consider the product, direct product set. That is usually denoted by this product Vi, I in I. So, the elements this is also called a Cartesian product. So, you can think of elements of this Cartesian product as a tuples. So, they are I tuples. That means like this Vi, I in I. The elements of this set are I tuples. You see, if the set I is countable, then you can still be write this as 1 to n and so on, you can denote the tuples. But when the set I is typically, let us say, real numbers or intervals, then we do not know which element will come first and which element will come later. So, only you can think of them as the tuples with ith position, and we do not know which is before earlier position and later position. So, the positions are numbered by the elements of I. So, on this obviously there is a group structure is obvious, that is component wise addition of I tuples. That is, if I have one I tuple Vi, another I tuple Wi, then the result should be another I tuple. And what is the ith entry here? You add the corresponding ith entries. So, Vi plus Wi, and this sum we are taking in a vector space Vi. So, this sum I will say in the vector space Vi. So, this defines an addition, and it is also again very easy to check that with this addition these Cartesian products become abelian group. If you want the inverse of the tuple Vi, you just take the inverses of Vi at the ith position, and the additive identity will be just 0 0 0 0 everywhere. All the tuple, all the entries are 0 0 0 at the ith place should mean 0 vector in the vector space Vi. Scalar multiplication also component wise. Also component wise. That is, if I have a scalar A and if I have a tuple Vi, this is in the product set, Cartesian product, then A times Vi, A times the tuple is same as, by definition it is, you push that scalar inside. So, A times Vi, and this is a scalar multiplication in Vi. So, with this Cartesian product becomes again a vector space. This Vi is a K vector space. Here I should mention that I am not checking the properties that we need for vector spaces 1 to 4, but they are so natural that more or less they are obvious, but the first time participants should check this on their own. This product vector space is called direct product of the family Vi I in I. Now I want to construct a new vector space from there, from this direct product. So we have this Cartesian product. So I don't take all I tuples. I will consider only those I tuples Vi in the product which have the property that almost all Vi are 0 for almost all I in I. That means only finitely many ith entries are non-zero vectors in Vi's. All other ith entries in this tuple are 0 vector in the corresponding vector space Vi. So this I want to give a name for this subset. This is a subset of this. This is, for example, this name I want to give is sum plus with a circle around it and I in I. This is Vi. You will see why do I denote it by the sum. Now what do you need to check that? Actually it is the same addition and same scalar multiplication, namely the component wise, also make this as a vector space. So I will just check that component wise addition and component wise scalar multiplication makes this direct sum a K vector space. This vector space is called direct sum, of the family Vi I in I. Okay, let us little bit illustrate. For example, when I is a finite set, special case, I is finite. Let us say I is 1 to n. And that means what? We have given a vector spaces numbered by V1 to Vn or k vector spaces. Then we have on the product V1 cross Vn. This is a product set. This is a k vector space. Component wise addition and component wise scalar multiplication. In this case, what is the difference between these two? There is no difference because there are only finitely many vector spaces are given. So, every tuple is almost all vectors in the tuple are almost all 0. Only finitely many can be non-zero. So, where now everybody is allowed. So, therefore, in this case direct product and direct sum are same. So, in this case when I is finite, the concepts direct sum, direct product and direct sum, these two concepts are identical. But obviously when I is not finite, let us take one case, I not finite. So, let us take a very simple case where I is infinite. So, the simplest infinite set is the set of natural numbers, which is the simplest one. This is 0, 1, 2 and so on. So, in this case we have given, and let us take a case where all our vector spaces Vi for any I in n, the vector spaces Vi, let us take them all to be real numbers. Real numbers. And let us take the field also to be real numbers. So, each Vi is a R vector space and we have given countably many. They are numbered by V0, V1 and so on, Vn and goes on. And each one of them is R. And the product means what now? Cartesian product means product of Vi, I in n. Now you can, because all these are same, so this you can think it is mapping from n to R, because each mapping F will correspond to which tuple? As I said, F of I in n. Given a n tuple, you have a mapping from n to R, and given a mapping, you have a tuple numbered by n. So, these as sets they are same. So, and what is the vector space structure? Component wise addition and component multiplication. So, this is nothing but, in earlier example we have taken arbitrary set I and the field and then the functions from I to that field, the same vector space structure here. So, this is nothing but the function space in fact. If you see what are the elements, elements are actually real sequences in real numbers. So, this is consisting of, this is sequences, elements are sequences in real numbers. So, elements are precisely the functions, and functions from n to R are precisely the sequences from, they are sequences in R. Each sequence in R xn, where xn's are real numbers. So, you can think them as functions x, where value of x at n is xn. So, and there is nothing special about this one. It's for so note that for arbitrary set I, if I take the family Vi to be a fixed vector space V, this is a fixed vector space, fixed K vector space. Then the product set, Cartesian product, you can think it is a function from I to V. Any function here f, you can think a tuple f of I, and any tuple you can think of the function. And what is the structure here of a vector space? It is a component wise addition and component wise multiplication. Addition and component wise scalar multiplication. These new vector spaces are very useful. Going back to earlier example where in this r power n. So, what is the direct sum? This is the direct product. This is the direct product of n copies of R. So, for instance, the sequence, the constant sequence 1, 1, 1, 1, 1, all the way 1, this is an element here. But this is not element in the direct sum. Because for an element in a direct sum, the characteristic property is only finitely many entries in this tuple should be non-zero, but in this all the entries are non-zero. So, it cannot be element in a direct sum. So, in this case the direct sum I am going to denote by r power n, but I should distinguish. So, I will put a bracket here, round bracket. So, this is the set of all sequences n in r power n such that n equal to 0 for almost all n. This is precisely the direct sum. The direct sum of the family Vi, each Vi is R and I is varying in n, R vector spaces. These two concepts are very important. So, let me again repeat the notation for the special case, the particular case. So, again note the special case. Take K to be any field and take I to be any set, and remember on the function space is K power I. They are all functions from I to K, and among those functions I take the functions who has only finitely many non-zero elements in the corresponding tuple, that I am denoting K power round bracket I. This is a subset here in the notation. This is all those f from I to K such that f of I equal to 0 for almost all I in I, and this is proper subset if I is not finite. So, this is a direct, this is I fold direct sum of K and this is I-fold direct product. And of course, when k is finite, both these are equal. K finite, then k power I round bracket I equal to k power I. This you will see that this notation is very, very convenient. Okay, so I want to make one remark. One remark I want to make. This is a little bit more general, so it is a concept of modules. We will not deal much about modules in this course, but it will be very convenient to know what it is, because and this is the right place, because all that remember that to define vector spaces we need a scalar field. So, one might ask what happens if the scalars are not field, they do not form a field, but for example they are only integers, or more generally what happens if one replaces a commutative ring instead of a field. Well, obviously the study will become more complicated, because we know in a commutative ring all non-zero elements need not have their inverses. So, in particular when you want to study linear equations, we cannot simplify by using the by cancelling the elements, dividing by them and so on. So, the study will become more restrictive even if you take so called ring of integers. Because in this ring the only invertible elements, when I write cross here, invertible elements with respect to the multiplication, there are only two of them, plus minus 1. So, if your coefficients are not 1 and bigger numbers, then you cannot cancel them, and then the study will become more complicated. But the definition still makes sense. So, definition of K vector space still makes sense. So, when I say this, the K means now K is not field but R vector space, let us say. So, R is any commutative ring. So, what is an R vector space? It is an abelian group V plus with a scalar multiplication of R on V. So, that is a map from R cross V to V. I will use the same letter A comma V goes to AV, and satisfying properties 1 to 4 of vector spaces. Saying this simply means that the ring structure, abelian group structure on V and the scalar multiplication on V, all these three are compatible with each other. Because in the definition, if you note, we never use the fact that K is a field, we have only used the fact that it is a ring. So, but to distinguish the two concepts, one calls instead of R vector space, to distinguish or to remember that our the base or the scalars, they need not form a field, but they form only a commutative ring. So, that will be noted by saying R module. So, instead of using the term R vector space, one usually use the term R module, where R is any commutative ring. And in this case, one also calls R is a base ring. Or even in the case of vector spaces, one calls that K as either a scalar field or also called a base field. Okay, so, the study of modules is obviously much more complicated than the study of vector spaces, and we will not get into this. Even for the simplest commutative ring, Z ring of integers, the study is not as simple as that of a vector space. So, I just wanted to make this remark and go on. Okay, so, the next one. Next one, I want to introduce the concept of subspaces. See, so far we have sets and subsets. If X is a set, Y subset just means that every element of Y and every element of X, and there is no other structure on the set that we are considering. So, for example, when we say a group G, G is a group, and then a subset H. When do you call this H as a subgroup of G? When the same operation of G, when we restrict to this H, with that operation H should become a group in its own right. So, let us record this formally. So, definition: a subset H of a group G is called a subgroup of G if the binary operation of G should induces a binary operation on the subset H. That simply means, see here you have a binary operation, it is a map from G cross G to G. This map we can always restrict to the subset H cross H, because H cross H is a subset here, but its image should go inside H. Then only its binary operation induces a binary operation on H, and with this binary operation this restricted binary operation H is a group. That means it should have identity. It should, every element, first of all the binary operation is associative, is obvious because it is restriction. It should have identity, but it is obvious that identity of G will also serve as identity in H, and inverses should also belong to H. So, how do we check somebody is a subgroup? That we have to check that if you have an element in H, the inverse of that element, which is a priori an element in G, should also lie in H. Then only an identity should belong. So, the two things we need to check, I will just note it. Identity of G, EG should belong to H, and 2, if A belong to H, then A inverse should belong to H. And obviously, I have before that already we have assumed that I will write it as a 0. It says if A and B are two elements in H, then A times B should be an element in H again. This 0 condition means the binary operation induces on H. Okay, so maybe this is a good time to stop. We continue next time. Thanks.